All right, let's dive into one of the most mind-bending, powerful, and frankly, most expensive substances in the entire universe, antimatter. Now, forget definitions for a second. I just want to start with a number. $62.5 trillion. Just let that sink in. That is more than double the entire annual economy of the United States.
So, what on earth costs that much? Well, that's the estimated price tag for a single gram of antimatter. It is, by a huge margin, the most valuable substance we know of. But what could possibly justify that cost? Well, the answer is simple: pure raw power.
That incredible value, it all comes down to antimatter's completely unique ability to turn mass, all of its mass, directly and perfectly into energy. It's the ultimate fulfillment of the most famous equation in all of physics. So what exactly is this stuff? The easiest way to think about it is like matter's perfect mirror twin. Every particle you can think of, like a negatively charged electron, has an antiparticle, in this case, a positively charged positron. It has the same mass, just the opposite charge. And here's where it gets crazy. When these two mirror images touch, they don't just bounce off each other. Nope, they completely annihilate, converting 100% of their mass into a massive burst of pure energy. And the scale of that energy release, it's almost impossible to wrap your head around. I mean, look at this. If we say a normal chemical reaction gives us 1 unit of energy, nuclear fusion, the power that fuels the sun, is 2.4 million times more powerful. But antimatter annihilation, that's 640 million times more powerful. It's not even playing the same game.
To put that in really stark terms, just 1 gram of antimatter touching 1 gram of regular matter would release the energy of a 43 kiloton explosion. That is 3 times the power of the bomb that fell on Hiroshima, all from an amount of stuff that would barely fill the tip of your pen.
But this incredible substance, it wasn't first discovered in some high-tech lab or a bomb test. No, it was first imagined on a blackboard, hidden inside an equation. And that's really where its story begins. Back in 1928, the physicist Paul Dirac was working on an equation to describe the electron, but the math kept giving him this weird puzzle. It's kind of like this. If you have the equation x squared equals 4, you know there are 2 answers, right? Positive 2 and negative 2. Well, Dirac's equation did the same thing. It gave him 2 solutions for the electron's energy. Instead of ignoring the weird negative one, he had the guts to say, hey, what if that actually represents a real particle, an anti-electron? And Dirac's wild idea kicked off this slow, patient, century-long journey of discovery. Just 4 years later, boom, the positron was found hiding in cosmic rays. Then, decades after that, the antiproton. It actually wasn't until 1995 that scientists at CERN finally managed to create the first complete antiatoms. And, just this year, they've had a huge breakthrough, figuring out how to trap thousands of them in a single day. So what does this annihilation actually look like up close? Well, it's not just a clean flash of light. It's more like a tiny, violent chain reaction. When the particles meet, they create a whole cascade of other short-lived particles. But here's the catch. Some of these particles, called neutrinos, are like tiny ghosts. They barely interact with anything. They just fly away, taking about half of that incredible energy with them, completely lost to us. Okay, so if this stuff is so unbelievably powerful, why aren't our cars and cities running on it? Well, that brings us to the absolutely massive trillion-dollar challenge of actually making it. That $62.5 trillion price tag, it has nothing to do with the cost of raw materials. It's all about staggering, mind-boggling inefficiency. To get just 1 unit of energy out in the form of antimatter, you have to pump about 1 billion units of energy in. All of humanity's efforts over decades have produced less than 10 nanograms. I mean, at the rate we're going, making a single gram would take 100 billion years. Just think about the power bill. CERN's particle accelerator, which is basically the world's only antimatter factory, eats up enough electricity to power an entire city. And all of that is to create amounts so tiny you have to count them in individual atoms. And let's say you actually manage to make some. You immediately run into an even bigger problem. Where do you put it? You can't just stick it in a jar, obviously. The second it touches the walls, boom, it's gone. So scientists have to use these incredibly complex magnetic bottles. They hold the antiparticles suspended in a near-perfect vacuum, cooled to just 4 degrees above absolute zero. Right now, the record for holding onto them is a little over 90 days. So these engineering challenges are just immense. But, they lead us to one of the biggest, most fundamental questions in all of science. Understanding antimatter is actually the key to understanding why we and this entire universe even exist.
Okay, so here's the cosmic mystery. Our best theories tell us that the Big Bang should have created matter and antimatter in perfectly equal amounts. But if that happened, everything should have instantly annihilated everything else in a universe-ending flash of light, leaving, well, nothing. So the big question is, why is there something instead of nothing?
The best explanation we've got is something called CP violation. It basically suggests that the mirror between matter and antimatter isn't perfect. There's a tiny, tiny crack in it. The laws of physics work just a little bit differently for each. And that tiny imperfection was just enough to let a small fraction of matter survive the great annihilation at the dawn of time. And get this, in a massive breakthrough this year, scientists at CERN saw this happen for the first time in baryons. Now, baryons are the family of particles that includes the protons and neutrons that make you and me. They found that one of these particles decayed at a rate that was 2.45% different from its antimatter twin. That's the first real hard evidence we have for why we're all here. So as we start to solve these mysteries and as we get just a little bit better at making this stuff, what does it all mean for our future? Well, the possibilities are nothing short of world-changing. And this is where you see the incredible two-sided nature of antimatter. On one hand, it's the only power source dense enough to ever make interstellar travel a real possibility. On the other hand, it's a tool so precise it could completely revolutionize how we treat cancer. I mean, just look at the potential leap in space travel. A chemical rocket gets us to, a tiny fraction of 1% of light speed. But a hybrid engine, one that uses just micrograms of antimatter to kickstart a bigger fusion reaction, could get us up to 5% the speed of light. That would turn a decades-long slog to Pluto into a trip of just a few months. But what if we didn't have to make it? What if we could just go out and find it? Some studies suggest that cosmic rays are constantly creating antiprotons naturally, and that they get trapped by planetary magnetic fields. It's estimated there could be almost 80 grams of the stuff just floating around between Venus and Mars, waiting to be collected. Mining space for antimatter might just be easier than making it on Earth. And then there's the medical side, where antiprotons could be a total game changer. They are over 4 times more effective at killing cancer cells than even our best current therapies. And that's because they deliver this incredible 1-2 punch. You get the precision targeting of a proton beam, followed by a tiny, localized annihilation event right inside the tumor, destroying it with almost no damage to the healthy tissue around it. So, from a strange quirk in an equation to the key to our cosmic origins, and maybe, just maybe, our future among the stars, antimatter really is the ultimate frontier. The challenges are enormous, no doubt about it. But the rewards? They could redefine what it means to be human. Is mastering it the final hurdle to becoming a truly interstellar civilization? It's something to think about.